Hello everyone, in this presentation, I will discuss about refrigeration and air conditioning system focusing on their performance and sustainability. For the problem statement, as we know, refrigeration and air conditioning system are widely used in residential, commercial and industrial application and they consume a significant amount of electrical energy. The performance of this system is commonly evaluated using the coefficient of performance or called as COP. The Carnot refrigeration cycle represents the maximum theoretical COP that can be achieved between two temperature reservoirs. However, this cycle is ideal and cannot be realized in a real-life application. In practical systems, refrigerants such as R134A are commonly used. Although R134A systems operate reliably and widely implemented, the actual COP is lower than the Carnot COP due to real-world loss such as friction and heat transfer irreversibility. In addition to formal limitation, there are also environmental concerns associated with R134A, particularly its high global warming potential (GWP). Therefore, it's important to study and compare both the performance and sustainability of ideal and practical refrigeration systems. Next, we move to objective and the scope of study. The first objective of this study is to calculate and compare the COP of vapor compression refrigeration system using R134A with the ideal COP predicted by the Carnot cycle. The second objective is to assess the sustainability of alternative refrigerants such as R744, R717, R790, particularly in terms of energy efficiency and global warming potential (GWP). In this study, we evaluate a vapor compression refrigeration system using R134A as the primary refrigerant. The system performance is then compared with the theoretical Carnot COP to highlight the gap between ideal and real system. From a sustainability perspective, alternative refrigerants which are lower GWP such as R744, R717, and R290 are also considered. Additionally, the scope includes system optimization such as improvement in compressor and insulation to extend the overall COP. For the literature review, in previous study have shown a significant difference between Carnot COP and real system COP, mainly due to the heat loss, irreversibility, and friction within actual system. Research comparing R134A with alternative refrigerant indicate that R744 offers strong environmental benefit, but it require higher operating pressure which increase system cost and complexity. Furthermore, sustainability study emphasized that replacing high GWP refrigerant with a low GWP alternative is essential to reducing the environmental impact of refrigeration system.
Hi, I'm Shafi. I'm building on the project scope Shaki introduced. My responsibility was to develop the research method and experimental design to evaluate the efficiency of our refrigeration system. We utilize the Carnot refrigeration cycle equation as our theoretical framework. As you can see on the screen, the coefficient of performance or COP is defined as the ratio of maximum heat supplied to the work required. We choose this specific equation because the Carnot cycle represents the highest absolute level of efficiency any real refrigeration system can theoretically reach. By establishing this ideal benchmark, we can later have ARIFFIN analyze exactly how far off real world behavior is from the ideal. For our experimental design, we use the thermodynamic property data for the refrigerant R134A. To ensure accuracy for ISMAYN incoming calculations, we selected evaporator and condenser temperatures based on typical operating condition. It is important to note that all temperature values were converted to Kelvin to satisfy thermodynamic calculation requirements. To create a workable model, our team agreed on several critical assumptions. First, the system is assumed to operate according to the Carnot cycle, implying perfect heat transfer and zero mechanical loss. Second, we assume perfect gas behavior for R134A, which simplifies the complex relations between temperature, pressure, and enthalpy. Third, We neglect all internal, external irreversibilities, meaning we are not accounting for pressure drops or heat leakage to the environment in this specific model. Finally, the third one, we assume steady state condition. This means we assume a constant operating temperature and steady state heat transfer with no transient fluctuation. This parameter provide the clean data set that ISMAYN needs to model the heat exchange and compressor work input.
Next part for analysis is about coefficient of performance, COP. A key thermodynamic challenge is determining how effectively a refrigeration system remove heat from a low temperature space relative to the work input. So here, it used as a primary performance indicator. COP we use to analyze the performance of refrigeration system by determining the ideal COP of refrigeration, the COP based on reverse Carnot cycle. Next, COP refrigeration, R134A. As you can see here, the formula is heat absorbed from the low temperature over worknet and used to achieve through the input of external energy to transfer heat from a cold body to warmer one. So also it consists of four basic processes that operate continuously to remove heat from a low temperature space and reject it to a high temperature surrounding. Next, four basic process. So the first one is process 1-2, where it is heat absorption. As you can see that heat from the refrigeration space at low temperature producing the cooling effect. Next, process 2-3, compression. It is where is the compression happen and higher pressure and temperature by supplying external work. The third one is process 3-4, heat rejection, where heat height is rejected to the surrounding. And next one, process 4-1, expansion, where it undergo a pressure drop through an expansion device. Next one is COP of refrigeration Carnot, where the formula is 1 over temperature high over temperature low minus 1, where it reverse heat engine that operate within two given temperature can only be as efficient the reverse Carnot heat engines. So the next one is about four basic process for Carnot. The first one is isothermal heat absorption at low temperature, where it absorbs the heat from a cool space at constant low temperature. Next one is isentropic compression, where it's compressed without heat transfer and it increases the temperature from low to high. Next one is isothermal heat rejection at high temperature, where it releases heat to the surroundings at a constant high temperature. The last one is about entropic expansion, where refrigeration expands without heat transfer. Is different formula with the Carnot COP for refrigeration. So the first one, we use the COP for R134A and apply the formula and we get the answer. Next is COP for Carnots, where the formula is given TL over TH actually is same with the 1 over TH over TL minus 1. That's all. Thank you.
For interpretation of the results, the calculation shows that COPR for refrigerant R134A is 6.25 while COPR for Carnot cycle is 9.0. There is a very clear difference between two values. The reason behind this is the fact that refrigerator in real life functions in an irreversible cycle while refrigerator in Carnot cycle works in an ideal, totally reversible cycle in which we could assume it to have no friction, no pressure drops, and highly efficient heat transfer. In real life refrigerator, inefficiencies from heat exchangers occur by having the evaporator to function at a lower temperature than ideal, which then reduces COP. An evaporator works by absorbing heat from the inside of the refrigerator to the outside refrigerator. For an evaporator to function properly, the refrigerant must be at a lower temperature than the refrigerated area. On top of that, heat leaks can happen in refrigerators. This is possible due to the imperfections of the refrigerator insulation system. Depends on the quality and thickness of the insulator used, temperature of the room can also dictate its effectiveness. If the room is hot, more heat can leak in and more heat leaks can enter the refrigerator, which causes the compressor to run longer and results to a higher work output, thus leads to a lower COP. Last but not least, we know that refrigerant flows through pipes, valves, evaporators, and condensers. As the refrigerant flows through the system, it rubs against the inner wall of the pipe. This phenomenon is called fluid friction. During this process, the refrigerant loses its pressure, which then results to the compressor needing more work in. More work in equals to lower COP value. One of the solutions to the said problem is to increase the evaporator temperature. This is done so that the difference between condenser pressure and evaporator pressure becomes smaller. Thus allows compressor to use less work to compress the refrigerant. Better cooling effect and lower work means higher COP. Then we can also improve insulation of the refrigerator to lower the chances of heat leaks into the refrigerated area. This will result to less cooling load on the compressor, which then leads to less work in and a higher COP. Moreover, proper maintenance is necessary to allow the system to run smoothly and efficiently. Dirty condenser coils and refrigerant leaks can severely impact the efficiency of the refrigerator. Proper maintenance ensures lower resistance and heat gain in the system. This will make sure that a higher COP can be achieved throughout the system. Aside from the given solutions, alternative refrigerants can also be used. For example, refrigerant R290 is also good alternative as it is widely used in the industry, has higher COP than refrigerant R134A and is cheap to operate. Refrigerant R744 is also suitable as it is natural refrigerant, non-toxic and is environmentally safe. Finally, the use of refrigerant R717 is a good choice as it is widely available, low cost, and has excellent efficiency.
Now, let's bring together our conclusion with key findings and the challenges we face in refrigeration system design. First, let's look at system efficiency. Our analysis shows a significant gap between the other Carnot cycle, which give us a COP of around 9.0, represent the theoretical maximum efficiency. However, real-world system only achieve a COP of about 6.25. This difference isn't small. It's nearly 31% efficiency loss due to friction, heat transfer losses, and irreversible thermodynamic processes that occur in actual systems. Now, how do we actually close this efficiency gap? Our research identifies 4 key system improvements that can significantly boost real-world COP closer to theoretical values. First, increasing the evaporator temperature. By operating at higher temperature, we reduce the compressor work required and directly improving the COP. Second, minimizing pressure drop throughout the system. Every pressure drop in components represents wasted energy that reduces overall efficiency. Third, improving insulation and reducing heat gain. Better insulation means less cooling load, which translates to lower energy consumption and improved system performance. And finally, a proper system maintenance. Regular maintenance ensures components operate at peak efficiency throughout the system lifetime. Poorly maintenance system can lose to 20 to 30% of its efficiency. But system improvement alone aren't enough. We also need to address refrigerant selection, and this is where things get complicated. This table reveals the central challenge: sustainability and safety are often in tension with each other. Take R744 or CO2. It's environmentally excellent, natural, non-toxic, and minimal global warming impact, but it requires extremely high pressure system, which means higher equipment costs and more complex engineering requirements. R290 propane is incredibly energy efficient and has very low global warming impact. But there's a critical problem: it is highly flammable. This makes it unsuitable for many applications, especially in densely populated areas or spaces with poor ventilation. And R717 ammonia, which is excellent efficiency and environmental profile, but it is very toxic and nearly could pose serious health risks, requiring extensive safety training, leak detection system, and strict regulatory compliance. As we wrap up, we see the reality: the gap COP efficiency is more than just numbers. It's about the energy we waste and the impact it has on our work. But there's a hope. By making simple yet powerful changes, we can make a difference. The environmental cost of refrigerant like R134A, with its high global warming potential, remind us that our choices matter. It's about our responsibility as engineer, as global citizen, to design system that serve humanity without destroying the planet we all share. The decision we make today in refrigeration can help shape a better, more sustainable world for tomorrow. Thank you for watching.